It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other,
where you put your knowledge to test
and battle it out with a test
to bring out the best in you. Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
So welcome to Unacademy Semester Exams, and we are dealing with the control systems quick revision for semester exams, chapter 3 as a part of lecture 5. So I want everyone to mark your presence here. I'm sorry. So before that, let me tell you about myself. I'm sravan Kumar, having 7+ years of teaching experience, mentored more than 5K students and cracked GATE. Unacademy, let's crack it. Crack GATE and ESE with India's largest learning platform and get subscription. And install Unacademy learning app from Google Play Store, and you get the daily live classes, structured courses, live test and quizzes, and unlimited access as well. And personalized coach, study tracker, question and answers, mains, all benefits of Plus and Iconic subscription. And in Plus subscription, you get the daily live classes, structured courses, live test and quizzes, and unlimited access as well. You can learn from the top educators of the Unacademy. You can see also you have GATE and ESE batches and year-long courses and all the specializations and courses. If you are opting for Plus or Iconic subscription, you can see all the benefits of Plus are present in the Iconic, along with personal coach, personalized test, study planner, and preparatory study materials. So if you are opting for Iconic subscription, then you can use my code YSK10 to get the maximum discount on your subscription, and this too for a limited period of time. And also if you are going for an Iconic subscription, which is the suggestible one for 24 months, you can use my code YSK10 to get the maximum discount on this, and this is valid for a limited period of time as well. So hurry up, and today we'll discuss control systems chapter 3. First, I'll tell you what are the different topics that we have in this, and I have segregated this into two parts as part A and B. As you know, we'll do that every time. So chapter 3, I have segregated it as part A and part B. Now today we will discuss Bode Plot. So let me write first all the topics that you have. This chapter 3 is time response analysis. Sorry, this is frequency response analysis. Sorry, this is frequency response analysis. In this frequency response analysis, you have the relation between time and frequency. I'll just write the topics and we'll discuss the important ones that are for the semester exams. Relation between time and frequency response. You have Bode plots and polar plot. Then you have Nyquist plot. So this is your syllabus. You also have the relative stability. Now let's see what are the important topics in this. I want everyone to mark your presence. Do like this video and also share this video with your friends and ask them to join. Inform everyone to join the session. This is one of the important questions that we are going to discuss today. We'll, as per the time permits, we'll discuss the Bode plot. I'll also tell you about the frequency response also. Because we are going with question and answer session, I would like to just emphasize on some points, like some short questions as well as the long questions that are generally asked in your examinations, right? So I want everyone to mark your presence in the chat box. Also do like, comment and share this with your friends and ask everyone to join the session. Now let's move ahead because we want to learn it as question and answer session. First, before that, I'll just give you some introduction about this frequency response analysis. If any system, any LTI system is subjected to a sinusoidal input, let's say a sine omega t, its output is also sinusoidal. I'm not getting into details. This is b sine omega t plus phi. The only difference between this input and output would be the magnitudes and the phase angles. The phase angle would change and the magnitude would also change in this, right? Good evening Meghana, good evening Sanjana. Very good. Also ask your friends to join the session. This is going to be a very important session, Bode plot. Many of you will be confusing in this particular topic. We'll learn 2 or 3 questions on this Bode plot today, at least 1 or 2 questions as per the time. So any LTI system subjected to a sinusoidal input will give you a sinusoidal output but with a different magnitude and a phase angle. Good evening Hasya, welcome to Unacademy. Very good. Now I'll also tell you some of the things like you have gain crossover frequency. Right, there is one question I can see, define gain crossover frequency and phase crossover frequency. So let's try to first learn what is gain crossover frequency. What is this gain crossover frequency is, see, as I told you, this is a frequency response that nothing but you will vary omega from 0 to infinity and observe the magnitude as well as the phase angle of the given function. So Kishore, good evening, welcome to Unacademy. So we'll observe the variation of this magnitude and phase angle with respect to frequency. So as I told you, frequency you are varying at a particular frequency. At a particular frequency, what happens is the magnitude, let us call it as m, is either 1 or in dB if you want to write it, it is 0 dB. So at that frequency, at a particular frequency, this magnitude is becoming 1 or 0 dB. That frequency we call it as gain crossover frequency. What is gain crossover frequency now? It is the frequency, it is the frequency at which the magnitude is 1, or we can say it is 0 dB. Magnitude of a given transfer function is 1 or 0 dB. This is the gain crossover frequency. Let's move on to the second one. I'll also explain these things once again next using some graph. Frequency, phase crossover frequency. You have two terms, one is gain crossover frequency, other one is phase crossover frequency. You have two things, one is gain crossover frequency, the other one is phase crossover frequency. And you'll vary omega, right? And you'll observe magnitude and phase angle. Now because this is phase crossover frequency, I'm only bothered about the phase angle. Now at a particular frequency, what will happen is this phase angle is equal to minus 180 degrees at a particular frequency. So at the frequency, what is phase crossover frequency now? The frequency at which phase angle is minus 180 degrees. So this is gain and phase crossover frequency, which is asked in one of the question papers of your semester exams. Now let's also see something called as third one, gain margin. You can also denote it this by kg, or you can denote it by gm. Now what is this gain margin is? It is actually, it is the allowable gain that can be introduced into the system to bring it to the, to bring system to verge of instability. That means you may not understand this like this. You can say it is the increase. You can also define it something like this. It is the allowable, it is the increasing or decreasing of gain without making it unstable. This is what is the actual meaning. And you can define this gain margin like this and write gain margin kg is equal to, it is also the reciprocal of magnitude of g of j omega into h of j omega at phase crossover frequency. We have written just now phase crossover frequency. This is denoted by omega pc or omega pcf, phase crossover frequency. And gain crossover frequency, you denote this as omega gc or omega gcf, right? Now this is gain margin, or in Bode plot you can write gain margin as gain margin is equal to 0 minus plus or minus y. What is this y? This y is the magnitude at phase crossover frequency. What is y? Y is the magnitude at phase crossover frequency. Now let us learn what is phase margin. The fourth one is phase margin. What is phase margin? So you can also be asked a question like what is defined gain and phase margin? It is the allowable phase lag that can be introduced in a system to bring it to the verge of instability or unstability, or it is the increase or decrease, allowably increase or decrease in phase without making system unstable, without making the system unstable. Varsha, good evening. Welcome to Unacademy. Now this gain margin is denoted by, gamma, and you can write this gamma as phase margin. You can also write it as PM or phase margin, and gamma is equal to 180 plus 5 GC. This is, what is 5 GC? 5 GC is, you need to know that this is the phase angle at gain crossover frequency. This is the phase angle at gain crossover frequency. So finally you can write, this is what is important, gain margin is equal to 0 minus plus or minus y, and the phase margin gamma is equal to 180 plus 5 GC. This y is at PC, phase crossover frequency. These two are important to determine the stability of a system. These two are important to determine the stability of a system. Now let's look at how do you say that the system is stable or unstable based on these two. Now let us look at them. Now let us say you have a magnitude plot and a phase plot. So we will draw this Bode plot on a semi-log sheet. Semi-log sheet, and let's say this magnitude is something like this. It's given like this. Let's say yes, this is the magnitude plot, and the phase angle plot is this. Let us say, and this line that is taken as reference is a 0 dB line. We'll plot it on a semi-log, so it is a dB. And this line is taken as a, let us say this is minus 180 degrees. You have plotted a, this is magnitude of GH versus frequency log, and this is phase angle versus frequency. Now this at this point 0 dB, this magnitude is plot is intersecting this at 0 dB. This line we call it as a gain crossover frequency. The frequency, these are all the frequencies. The first line, let us say it is 0.01 or 0.1, and this will become the gain crossover frequency omega GC, because it is the frequency at which the magnitude is equal to 0 dB. So this is the magnitude, green color, which is intersecting 0 dB line. So this frequency is called as gain crossover frequency. And let us consider this point, and this frequency we call it as a phase crossover frequency. This is a omega PC. Can I say, because the frequency will increase from left to right, can I say omega PC is less than omega GC, or omega GC is greater than omega PC? Yes, yes. Now you can also say that, what is this? Remember that at gain crossover frequency, this is the line that you have drawn, right? This is gain crossover frequency. Extend it onto the phase plot and you'll have a phase angle. This is intersecting at this point. So this value is phase angle at gain crossover frequency. See, this is gain crossover frequency. On the same line, I'm just taking phase angle. This angle is called as phase angle at gain crossover frequency. So what can you write here? Phase margin gamma is equal to 180 plus phase angle at gain crossover frequency. So 180 plus, if you observe, this point is above this minus 180 line. That means it is greater than, this is greater than 180 minus 180. So what do you get? You'll get a negative gain margin. Yes. Now let us consider the phase margin, gain margin now. Let us say gain margin. What is gain margin is equal to? It is 0 minus plus or minus y PC, magnitude at phase crossover frequency. This is phase crossover frequency. Just you are dropping a line onto this magnitude plot and you got a magnitude, and this is a positive magnitude. So this is 0 minus of plus y. So this will be a negative. So here you have got both gain margin and phase margin as negative. Whenever this gain margin, phase margin are negative, we can say that the system is unstable. Any of this, either gain margin or phase margin. Vicky, good evening. Welcome to Unacademy. That is phase crossover frequency if it is greater less than gain crossover frequency, or if the gain crossover frequency is greater than phase crossover frequency, then the gain margin, phase margin. So you'll write it something like this. Can I write it this way? That if the phase crossover frequency is less than gain crossover frequency, or if the gain crossover frequency is greater than phase crossover frequency, then gain margin is negative and phase margin is also negative. Then can I say that the system is unstable? So you can say the system is unstable if the phase crossover frequency is less than the gain crossover frequency, or gain crossover frequency is greater than the phase crossover frequency. Right? Now let's look at the second case. Let us say you have a magnitude and phase angle lines like this. You have magnitude and phase angle. So this magnitude, let us say you have a plot like this, magnitude plot, and this is something like this. Let's say you have a phase angle. So let's say this is the phase plot. Now this is magnitude of G into H, and this will be a 0 dB line, and this will be minus 180 degrees. Now if you observe what is gain and phase crossover frequency, it is a frequency at which the magnitude, this green color top straight lines, is a 0 dB. Shiv Kumar, good evening. And minus 180 degrees, this is a phase crossover frequency. If you observe, in this particular problem, both gain and phase crossover frequencies are equal, right? So this is both, you can say, this is both gain crossover frequency and phase crossover frequency, and gain crossover frequency is equal. This is equal to gain crossover frequency, or we can say like this. So can I write phase crossover frequency is equal to gain crossover frequency? Yes. Now in that case, what will happen to gain margin and what will happen to the phase margin? Now what is that gain margin? It is 0 minus of plus or minus y. What is y here? If you just drop a line, it is 0 anyways. So this will be a 0, and this is 180 degrees plus phi GC. So this is also, if you drop a line from on this to this phase plot, this is 180 degrees minus 180 degrees, that's also a 0. So can I say this, in this case you can say gain margin is equal to phase margin is equal to 0 when gain margin is 0 and phase margin is 0 when gain crossover frequency is equal to the phase crossover frequency, and we can say that the system is marginally stable system. We can say that the system is marginally stable system. Let us consider the third case. Let us consider third case. Now let us consider, this is the plot. And this is, that is the magnitude plot, and this is the phase plot. Now if you observe in this plot, this is G magnitude and this is 0 dB, and this will be minus 180 degrees reference. Now what is this point? This is gain crossover frequency. This is gain crossover frequency. Drop a line. Now what is this? This is a phase crossover frequency. Just drop a line from this point. This is a phase crossover frequency. It is a frequency at which the magnitude plot intersects 0 dB is the gain crossover frequency. So I can write it as omega GC, and this is omega PC. As you know, frequency is increasing from left to right. Can I say omega PC is greater than omega GC, or omega GC is less than omega PC? Both are same? No. Can we say in this case, let's try to find gain margin and phase margin. So what is the gain margin? It is found, what is that? 0 minus plus or minus y at phase crossover frequency. So this is phase crossover frequency. At this point, if you observe the magnitude, you have some magnitude which is a negative value. So can I say 0 minus of minus y will be a plus y. So gain margin is positive. Gain margin is positive. Now if you observe phase margin, it is 180 plus phi GC. So 180 plus phi GC is phase angle at gain crossover frequency. This is the gain crossover frequency. And if you observe the same point, this is phi GC, phase angle at gain crossover. And if you observe this 5 GC, it is less than minus 180. So it is minus 5 GC less than 180. So this will also be a positive value. So phase margin is a positive value. Now if you observe, so in this case, when phase crossover frequency is greater than gain crossover frequency, or you can say gain crossover frequency is less than phase crossover frequency, gain margin is positive and phase margin is also positive. Therefore, you can say that the system is stable system. The system is a stable system. I would like to add one point here. If the students are not able to see the screen clearly, just click on the three dots on the right top corner of your screen, and when you click that, you'll have the quality. Just click on it. You have different auto 144p, 240p, 360p and 480p. You can click on 480p and the screen will be crystal clear. So finally, you can conclude one point: if the phase crossover frequency is less than gain crossover frequency, or if the phase crossover frequency is equal to gain crossover frequency, and if phase crossover frequency is greater than gain crossover frequency, in this case both gain margin and phase margin are negative and system is an unstable system. And if the gain margin, if phase crossover frequency is equal to gain crossover frequency, gain margin is 0 and phase margin is 0, and system is marginally stable system. Don't go away, stay back. We are going to solve a problem now from your previous university examinations. And in this case, gain margin is positive and phase margin is also positive. So then the system is a stable system. These are some of the points that you need to remember. Now let's take one question from the university question papers on Bode plot. Yeah, this is a question. Let's take one question that is previously asked in your question paper. Yeah, let's consider one question. So with this idea in mind, let's try to solve one previous university question. The question says, find gain margin, phase margin using, find gain margin and phase margin. This is one of the questions in your university question paper. Using Bode plot, using Bode plot for the open loop transfer function, for the open loop transfer function, g of s is equal to k by s into s plus 10 into s plus 2. This is the question. K by s into s plus 10 into s plus 2. So let's look at this question and just concentrate. We are going to solve this question. So read the question. You need to find gain margin, phase margin using Bode plot. So first one is Bode plot. This is one point that you need to observe from the question. Then we are asked to find gain margin and phase margin for the question. Right? So these are the two things that you need to find from the given question. And third, given transfer function is g of s is equal to k by s into s plus 10 into s plus 2. So let's try to solve this question. So first step would be, in the solution, the first step would be write given open loop transfer function, into a standard form, or you'll also call it as time constant form. right? So what is that time constant form? Just write this. First write g of s is equal to k by s into s plus 10 into s plus 2. So g of s is equal to k by s into 10 into 1 plus s by 10, 2 into 1 plus s by 2. Take common 10 and 2. You need to write in time constant, that is 1 plus st form. 1 plus st form. So this will be g of s is equal to k by 10 into 2, 20s into 1 plus, you can write this as 0.1 s, 1 by 2, 0.5 s. Right, so you can write g of s is equal to 1 by 20, 0.05 k by s into 1 plus 0.1 s into 0.5 s. Is this clear? Now second point, this is the first step. Now second step, let k is equal to 1 and sinusoidal, write the sinusoidal transfer function. So that is s is equal to j omega, sinusoidal form, sinusoidal transfer function. Now, how do you write that? We already know g of s is equal to 0.05 k by s into 1 plus 0.1 s into 1 plus 0.5 s. Now, you have to let k is equal to 1. This is g of s is equal to, can I write it as 0.05 into 1 by s into 1 plus 0.1 s into 1 plus 0.5 s. Yes. Now second, substitute s is equal to j omega. Can I say g of j omega is equal to 0.05 by j omega into 1 plus 0.1 j omega into 1 plus 0.5 j omega. Yes, you can do that. So this is the second step that you need to do. And third step, determination of corner frequencies. Third step, determine the corner frequencies. Determine the corner frequencies. Right? What are the corner frequencies? See, while doing this corner frequencies, these corner frequencies must be in ascending order, so that the time constants here should be in descending order. So first write g of j omega, then we'll do that, is equal to 0.05 by j omega 1 plus 0.1 j omega 1 plus 0.5 j omega. Now here you have 1 plus 0.1 j omega and 1 plus 0.5 j omega. This is 1 s into t, this is 1 t, you can say this is other t. This t should be in the descending order, so that you'll have omega in the ascending order. So what is this t? This should be in the descending order, so this should be t1, this should be t2. Therefore what is omega c1? That is 1 by t1, 1 by 0.5. Omega c2, 1 by t2, 1 by 0.1, 1 by 0.5, 2, and this is 10, so 2 radians, 10 radian per second. Clear? Now we have determined corner frequencies, and in this third step there is one more important thing that you have to remember, that assume one lower and one higher corner frequencies. You can assume it 1 by 10 times of this, or you can assume any other value. So assume one lower frequency and one higher frequency, such that, what is that condition you need to take is one frequency which is less than omega c1, one frequency which is greater than omega c2. So I'll consider omega L is equal to, let me take one value that we have already taken, 0.01 radian per second, and omega H is equal to 100 radian per second. Let us consider, you can consider 0.1 also, you can consider 1 radian also, doesn't matter. right? So what are the total corner frequencies? Let us write the corner frequencies now. Corner frequencies, what are the corner frequencies? Omega L 0.01 radian per second, omega C1 2 radian per second, omega C2 10 radian per second, omega H 100 radian per second. Now after this you need to, in order to draw magnitude plot, you need to, our task is to do something like this. For various values of omega, find the magnitude and phase angle. Find the magnitude and phase angle. So for that you need magnitude. So this is the fourth step. So let's consider the fourth step, magnitudes. So to find these magnitudes you need one table, because it's Bode plot is a straight line approximation. You need to construct a table like this, and I'll tell you what are the things that you need to incorporate in this. First is the term, second is the corner frequency, third is the slope and change of slope. Term, corner frequency, slope and change of slope. So term, corner frequency, frequency is radian per second, slope in dB per decade, and this is also in dB per decade. Now let's write what is the term. So in order to make you understand what is the term, I'll consider g of j omega. What is g of j omega that you got? 0.05 by j omega into 1 plus 0.1 j omega into 1 plus 0.5 j omega. You can split this as 0.05 by j omega as one term, 1 by 1 plus 0.1 j omega as the other term, 1 by 1 plus 0.5 j omega as the other term. So these are the terms. This is a term, this is a term, this is a term. Three terms. So write that. Sirisha, welcome. Welcome to Unacademy and welcome to Control Systems Quick Revision. So what is the first one that you can write? 0.05 by j omega. Does it have any corner frequency? No. S is equal to 0 does not make a sense. That is log 0 does not exist. Next, the next one that I have to take is 1 by 1 plus j 0.5 omega. Next, 1 by 1 plus j 0.1 omega. So this has a corner frequency 1 by 0.5 2 radian per second, 1 by 0.1 10 radian per second. You also have to write this in the such that you have to write these terms in an order such that the corner frequencies are in the increasing order. Now what is this slope? Every pole, remember this, every pole will offer a slope of minus 20 dB. Every zero will offer a slope of plus 20 dB. So if you observe, this is a pole denominator, this is also a pole, this is also a pole. So this pole, single pole, minus 20, single pole, minus 20, single pole, minus 20. Now we do not have any change of slope because we do not have any previous value. Now what is change of slope in the second case is, consider this slope and minus 20, add this to this, minus 20 will be minus 40. Similarly for the next case, bring this here, that is minus 40, and add the present slope, minus 20. So minus 60 is the change of slope. This change of slope is required. I'll just move this. Yeah, this change of slope is required to calculate the magnitudes. So let us go and find the magnitudes now. So how do you find magnitudes? We are finding magnitudes at corner frequencies. We'll just find at corner frequencies. Corner frequency is the frequency at which the two asymptotes meet or intersect. Now let us look at that, magnitudes at corner frequencies. So for the first magnitude, if you want to find, because it is in dB, you can write 20 log mod of g of j omega actually. But here 20 log mod, what we consider is, see this we are finding at omega L. What is that value? 0.01 radian per second. Now, if you compare 0.01 with 100 radian per second, this seems to be a very less frequency. So that is the reason we will neglect these two terms. Approximating this as 1 will neglect these two terms. We'll only consider this 0.05 by j omega. Once again, so we consider, when you consider this first and second frequency for both, remember for first and second corner frequencies, these are considered to be very less than the higher frequency, higher corner frequency, and we neglect these higher order terms, these terms. So we will only consider 0.05 by j omega. So we consider 0.05 by j omega. So what is the magnitude here? 20 log mod 0.05. Just remove this mod. What happens? Yeah, this is 0.05 by under root of omega square, that is omega. Now substitute the value 20 log 0.05 by 0.01. So this is 20 log 5. So if you substitute that, you'll get somewhere around 13.9. Check whether these are correct or not. I'm just giving you some uh, numbers. So this is the magnitude at, so at omega L is equal to 0.01 radian per second. Let's call this as M1. M1 is equal to 13.9 dB. Now let's try to calculate the next frequency. At omega C1, what is that? 2 radian per second. M2 is equal to 20 log mod, same 0.05 by j omega, that is 20 log 0.05 by omega. So that will give you 20 log 0.05 by 2. This value will get it as minus 32.04 dB. So at omega C1 is equal to 2 radian per second. At omega C1 is equal to 2 radian per second. M2 is equal to minus 32.04 dB. Clear? Now let's move to the next, because we have to find magnitude at all the frequencies. We have found at two frequencies. Let's consider the third corner frequency at omega C2 is equal to 10 radian per second. Only for the first two frequencies you will consider this. From the third frequency you will use this expression like M3 is equal to third corner frequency, right? M3 is equal to previous gain less change of slope into, this is the bracket, into log omega C2 present frequency by previous frequency. This is what you need to write. Now M3 is equal to, what is the previous gain we had? 32.04 minus 32.04 plus, now this change of slope is taken from the table, the first change of slope, that is you have to take, right? So this is minus 40 into log, what is the present frequency you have? 10. What is the previous frequency you have? 2 radian per second. So this will give you M3 is equal to an approximate number of minus 59.99, or I can write it as minus 60 dB. Therefore, can I say at omega C2 is equal to 10 radian per second? You just need to check these values. I'm writing some approximate magnitudes. So this is the magnitude at third corner frequency. Now let's take, so this is omega C2. Now let's consider at omega H. At omega H is equal to 100 radian per second. What is M4? M4 is the same value. You need to write, what is that? Same expression, previous gain plus change of slope If you have any doubts, you can ask me. You can interrupt me in the middle and you can ask me. Sirisha, Shiva, Vicky, Havarsha, Kishore, Hasya, Sanjana, Meghana, anyone if you have any doubts. Log omega h by omega c2. Right, what is M4 is equal to now previous gain. What is the previous gain? Minus 60 dB. Minus 60 plus change of slope. This change of slope is taken from this table. The only change of slope that is left is 60. Minus 60. Right, minus 60 into log, check whether these numbers are correct or not, because which I am writing it randomly, some approximate number. Present frequency 100 by previous frequency 10, so this is minus 119 or minus 120 dB. So at, can I write at omega h is equal to 100 radian per second, M4 is minus 120 dB. Yes. Now just make a table and write all these values in one table, so that will be easy for us while plotting the graph. Let us consider this now. This is the frequency or corner frequency. So this is for fourth one was magnitudes. So I'll write magnitude versus frequency. What is that frequency? Corner frequency. So this is magnitude. You can also call it as A or M. I'm just taking it as A or M here. So what was the first corner frequency? 0.01. This is radian per second and this is in dB. Second one was 2, third is 10, fourth is 100. Now for 0.01, what did we get? It is 13.9. For 2 we got it as minus 32.04 and we got it as minus 60 and this as minus 20 dB. So this is the magnitude versus frequency table. Now let's try to find what is the second thing that you have to do as a part of fifth step. Fifth step, phase angles that you need to find. So what is the phase angle? You need to write. For that, first write what is g of j omega. It is 0.05 by j omega into 1 plus 0.1 j omega into 1 plus 0.5 j omega. Remember one thing, that is if you have 5 at an angle 30 degrees into 3 at an angle 40 degrees by 7 at an angle 80 degrees, you can write this as 5 into 3 at an angle 30 plus 40 by 7 at an angle 80, and 5 3s are 15 at an angle 70 degrees by 7 at an angle 80 degrees is 15 by 7 at an angle 70 degrees minus 80 degrees. The point I would like to tell here is, if you have a multiplication, you can add these angles. You will add the angles. If you have a division, you will subtract the angles. You will subtract the angles. Just remember this concept. Now here I would like to write for each and every term. Let us call this as 0.05 plus j omega. So 0.05 plus j0. Find the angle of this. Next, angle j omega plus 0, second term. Next, angle of 1 plus 0.1 j omega. Find the angle. Angle of 1 plus 0.5 j omega. Find the angle. Now, so this is tan inverse b by a. 0 by 0.05 will get a 0 degrees, because it is tan 0, right? Tan 0 degrees. Next, this is tan inverse 0 by, sorry, imaginary omega by 0, that is tan inverse infinity, that is 90 degrees. If you have any doubts, I guess you are able to understand this. Varsha, Kishore, Asya, Sanjana, Shirisha. If you feel any difficulty, you can let me know. And if you are okay, you can just give me some yes or no, right? Now this is tan inverse 0.1 omega by 1, imaginary by real. So this is okay, sir. Very good. Tan inverse 0.1 omega. And this is tan inverse 0.5 omega by 1. Tan inverse b by a, right? If you have a plus ib, you can write it as Meghna. Clear, sir? No, sir. It's fine. Varsha. Thank you. So tan inverse b by a. So that's what we write, right? So this is tan inverse 0.5 omega. Now let's try to substitute all these values in this. So g of j omega is equal to 0.05 plus j0 by 0 plus j omega 1 plus zero point 0.1 j omega 1 plus zero point 0.5 j omega. Now angle of g of j omega is equal to angle of this 0 degrees, angle of 0 plus j omega 90 into this is tan inverse 0.1 omega into tan inverse 0.5 omega. So I'll call this as phi. So phi is equal to, can I write, if I take 90 to the numerator, 0 degrees minus 90 degrees. Tan inverse if I take, it is tan inverse 0.1 omega minus tan inverse 0.5 omega. No, phi is equal to minus 90 minus tan inverse 0.1 omega minus tan inverse 0.5 omega. So this is the phase angle. Now you need to find this phase angle at different frequencies. You need to find this phase angle at different frequencies. So let's try to find this phase angle at different frequencies. So phi is equal to minus 90 minus tan inverse 0.1 omega minus tan inverse 0.5 omega. Now at omega L is equal to 0.01 radian per second. Phi is equal to minus 90 minus tan inverse 0.1 into 0.01 minus tan inverse 0.5 into 0.01. Now calculate this phi. This phi will be phase angle if you try to calculate. This is approximately equal to minus 90 degrees. Now at omega C1 is equal to 2 radian per second. Phi is equal to minus 90 minus tan inverse 0.1 into 2 minus tan inverse 0.5 into 2. This will give you phase angle of minus 146 degrees. 146.3. So you can also approximate it to 146. Now let's try to find at other frequencies. What is phi is equal to minus 90 minus tan inverse 0.1 omega minus tan inverse 0.5 omega. Now at third corner frequency, at omega C2 is equal to 10 radian per second, phi is equal to minus 90 minus tan inverse 0.1 into 10 minus tan inverse 0.5 into 10. So if you find, you'll get a phase angle of minus 213 degrees. Yeah, minus 213.6. Very good. Minus 213. Let's write that. 213.6 degrees. Very good. Now at omega h, tell me at omega h 100 radian per second, phase angle is equal to minus 90 minus tan inverse 0.1 into 100 minus tan inverse 0.5 into 100. I want this answer. What is phi? For 100 radian, 263.1. Very good. Minus 263.1 degrees. Very good. Now let's try to draw a table and write all the values. Now let's try to write all these values. So let's try to write all the values for different corner frequencies. What is the phase angle? This corner frequency is in radian per second and this is in degrees. So can I write this fifth step as phase angle versus frequency? Yes, you can. So what is the first corner frequency? 0.01. Second 2, then 10 and 100. For 0.01, what is the value we got? Minus 90 degrees, minus 146 degrees, minus 213.6 degrees, minus 263.1 degrees. Very good. Now, when you know this magnitude and phase angles, you need to plot this on a graph. So I cannot exactly do that right now, I guess. So let's consider one plot. So I'll roughly draw one graph and I'll just tell you how does that look like. This is a rough sketch. So consider this as the first corner frequency and this as the 0 dB line. This has the 0 dB line and this line as the minus 180 degrees line. We'll assume this. You'll have some lines on this semi-log sheet. So I'll write this as 0.01 radian per second. Next line, I'll consider this line as the next one as 0.1 here. So let's say this is 0.1. This is 1 radian and this has 10 radians. You also have 100, right? So this has 100 radians. And so these values are, write these values. This is 0.1 radian per second. This is 1 radian per second, 10 radian per second and 100 radian per second. So this, what is this? Listen carefully. You may not be able to, you have a doubt of plotting this, I guess. So minus 180 degrees. Let's take minus 140 here and this has 100, 40 difference. And this has 40 if you had, it is 220 if you add, minus 260 I guess, and this has minus 300. Now this is 0 dB. Let's call this as 40 dB. This as minus 40 dB and minus 60. What are the magnitudes that you have? Just check the magnitudes. Minus 120 is also present. Oh god. So 60 plus 40, this is 100 and this is minus 140, right? I'm just separating this by a line like this. Now let's look at this magnitudes. You can, if you have the magnitudes, you can check that. I'm just trying to represent this. So at 0.01 you have, at 0.01 you have 13.9. so I'll just mark some point here. So at 0.01 frequency you have 13.9. now next at 2 radian minus 32. So this is 1 radian. We'll have another line. I'll just take one line here. Let's consider this line as, yeah, I'll consider this second line. This has 2 radian line. Because this is 1 radian, I'll consider this line as 2 radian. And on this 2 radian, what is the value that we have? Minus 32. So let us consider this as minus 32. So join these two lines by using a straight line. Right? It will intersect somewhere around at 0.4 actually. It is at 0 dB, it will not intersect that line. Right. Now, after this, the third magnitude is minus 60 at 10 radian. At 10 radian, minus 60. So you can consider this as this point and join these two. And at 100 you have minus 120. So this is between these two. So this is the point. So this is the point you have to join. So this is one point at 10 radian, at 100 radian, at 2 radian, at 0.01 radians. Now this will intersect the 0 dB line at some point like this. Yeah. Now next phase plot. At 0.01, what is that? Minus 90. So somewhere here, can I take it? Minus 90, this point at 0.01 radian. Next 2 radians, this is 2 radians line, this green color you can see. At 2 radians you have minus 146. So I'll take somewhere here minus 146, yeah, this point. Next, at 10 radians, this is a 10 radians line. You can see at 10 radians we have 213. At 10 radians we have 213. So can I take between these two? Because this is 220, I can take somewhere between these two, 220 and 263.1 at 100 radians. 263, I can just take some line here, this part at 100 radians. So I'll have to join all this, just join these points by just not by straight lines, by just a normal graph. Now if you observe this graph is intersecting 0 dB line at a particular point, and you will get actually that point as 0.04. This point that you draw, on an original graph sheet, if you just draw this line, you will get this point as omega gc is equal to 0.04 radian per second, right? So this is the gain crossover frequency. So what is that gain crossover frequency? This is omega gc, the frequency at which the magnitude plot will intersect 0 dB line, right? So this is gain crossover frequency. Now what is gain crossover frequency we got? Let us take this as 0. I'll write here, gain crossover frequency is 0.04 radian per second. Now what you have to do is just draw a line from this point, just draw a line from this point, and it will intersect this magnitude plot. It will intersect this magnitude plot at a particular point. See, this is intersecting this magnitude plot at a point. Yes, it is intersecting magnitude plot. And if you try to find, sorry, this point is intersecting phase angle plot at a particular angle, and if you find this angle, it will be approximately, if you just try to do it in an exact graph, this angle is phase angle at gain crossover, because this is gain crossover frequency. The angle that you find at this will be gain crossover frequency, and this gain crossover frequency will be phi gc, will be minus 90 degrees approximately. So what you have to do on this 0 dB line, 0 dB line is intersecting magnitude plot at this point. The same line you have to project it onto phase plot and find the angle phase plot on the phase plot. If you find this, you'll get phi gc, right? Now this, what is this point? What is this point? This is minus 180 degrees line, and this phase plot is intersecting minus 180 degrees line at a particular frequency. This frequency, let's call this frequency, and that frequency you get it as approximately, this frequency will be, this is called phase crossover frequency. It is the frequency at which this phase plot, the down yellow color line that you are looking, this is intersecting minus 180 degrees line at a frequency. This frequency we call it as, this is 6 radian per second, we call it as phase crossover frequency, because this is phase plot is intersecting minus 180 degrees. So can I say omega pc is equal to 6 radian per second? Now at this omega pc, see, this is phase plot. You just need to draw a line onto this magnitude plot and find the magnitude, and find this magnitude approximately, this magnitude. You need to find this magnitude at this point. What is the magnitude at this point? If you see, this magnitude approximately will be this is approximately, this will be 56 dB. If you just draw it on a clear graph, this is y, this distance from 0 dB, this distance is y. So y is equal to, you can write minus, because it is down of 0 dB. See, this is down, this is 0 dB line, so this is minus 56 line, so this distance is minus 56, right? Now from this information you can find gain margin, phase margin. What is gain margin? Is equal to 0 minus of plus or minus y. So 0 minus of, what is plus or minus y? It is minus 56. So this is 56 dB is the gain margin. Hope this is clear for you. Now what is phase margin? Phase margin is equal to 180 plus 5 GC. So 180 plus, what is 5 GC? You have minus 90. So this is 90 degrees. So we got phase margin and gain margin. That was the question, right? So if you just look at the question that is asked in the previous examination, so such a long question, I guess. Yeah. gain margin, phase margin were asked to determine. So we have found gain margin and phase margin here. So from this you can say gain margin and phase margin, it is not asked, but you can write are positive. Therefore, given system is a stable system. Can I write it this way? Yes. So this is how you will determine the gain and phase margin of a given open loop transfer function using Bode plot. I'll just move on the slides from the starting. Just look at them once again. If somebody is making a note of it, you can also make a note of it. But let's look at this question. So this is the question that we have solved. So someone who hasn't prepared till enough can just watch this video and you can attempt this question on Bode plot, which is very important and it is very frequently asked question in your university examinations. So please do inform your friends, share this video, ask them to listen to this and they will definitely get benefited out of this. Clear? I'll just move on the slides. If somebody is making a note of it, they can also make it. Now let's look at this. Find gain margin, phase margin using Bode plot for the given open loop transfer function. This is the first step, writing it in standard form, 1 plus st. Next we have written let k is equal to 1 and s is equal to j omega. You just move on this. I'll check for one more question from your university question paper and we can solve it, I guess. We have so the third step is determination of corner frequencies. You can find corner frequencies. And then we will assume one lower and one higher corner frequency. So these are the corner frequencies that we have finalized. So then we take the magnitudes. Let me take this. Yeah. And to do that we need to have some table like term, corner frequency, slope and change of slope. So we have done these different terms from this. We have taken these three terms and corresponding corner frequencies we have written. Yeah, sir, could you please explain again gain margin, phase margin, last step? Definitely, sure. Once we move on the slides, at the end I will definitely explain gain and phase margin again. So these are the magnitudes, corner frequencies, slope and change of slopes. Then we find the magnitudes at different corner frequencies. At first corner frequency we consider g of j omega, neglecting the other terms, approximating it as 1 because we are considering the low frequencies. For the first two magnitudes we do the same, and from the third corner frequency we just take previous gain plus change of slope into log omega c2 by omega c1. For the rest of them we take this change of slope from the table that we have considered. Then we have this table, we just make it magnitude versus frequency. Then we consider the phase angles, and this phase angle you have got it, phase angle expression. Then at different frequencies you find this phase angle, and we draw a table of phase angle versus frequency, then plot it. Now the simple thing that you have to do is, let me explain you clearly once again. You just have to do this thing. Let me tell you phase margin and gain margin from this. So this is, let us say you have a magnitude and you have a phase angle plot. So you have you got magnitude something like this now. Let's say this was the magnitude that we got actually. So this was the magnitude plot. Then we had a phase plot like this. It's intersecting at, so this was this, see, this frequency at which it will intersect, this is 0 dB reference, and this is magnitude G, and this is phase angle G. At 0 dB it is intersecting at a particular frequency. We call this frequency as omega GC, gain crossover frequency, and we are extending the same line onto phase angle plot, and we will observe the phase angle at this gain crossover frequency, and this we got it as minus 90. We call this as phi GC, phase angle. What is phi GC? That you need to understand first. What is phi GC? Is phase angle. First, phi is phase angle. What is GC? Gain crossover frequency at gain crossover frequency. This frequency is gain crossover frequency, and at this point if you extend on to phase plot, you will get an angle. That angle is called as phi GC. You need to note these two values. We will note what is omega GC, that we have noted it as 0.04 radian per second, and we have noted phi GC, phase angle, as minus 90 degrees. Is this clear now? Yes, you can, Hasya, you can approximate the values in the plot. That's not a problem, because Bode plot itself is an approximate plot. You cannot exactly mark the points. So Hasya, you can approximate the values in the plot. It's not an issue. And Soumya, good evening. Welcome to Unacademy. You are late, I guess. No, omega GC that you have got here, and yes, yes, Varsha, very good. Now, let us look at this. This is omega GC, right? You got omega GC and phi GC. You need to write like this. Next, we will consider this. First, we have just considered magnitude plot. Now, consider phase angle plot, blue line. This is intersecting at a particular point, and you have a frequency at this particular point. You have a frequency at this particular point, and this frequency we call it as phase crossover frequency. We call this frequency as phase crossover frequency. We have got this as 4 radian or 6 radian per second, I guess. Yeah, this was 6 radian per second. Now, if you extend this is phase plot. You are extending the same line onto magnitude plot, and at this point you need to find the magnitude, and this we got it as minus 56. This is minus 40, minus 20, minus 40, minus 56. This difference, this is y. So at this phase crossover frequency at omega PC 6 radian per second, we found y value, that is minus 56 dB. Y is minus 56. At that frequency, you need to find this difference of y, that is from 0 dB. What is the distance of this point? So you can find from this point, this measurement. This is y. So when you know these two values, we know these two. What is that? Omega GC as 0.04 radian per second, and phi GC, phase angle at this frequency, as minus 90 degrees. And we know omega PC as 6 radian per second, and y you need to find. You just need to project this line onto this magnitude plot and find this magnitude, and when you find this magnitude, it is minus 56 dB, and from this you can write gain margin we know it as 0 minus plus or minus y, and phase margin as 180 plus phi GC. That's the reason I have found y and phi GC. So substitute this value. Gain margin is equal to 0 minus, what is this y? Is it plus or minus? Minus. So what is the value? Minus 56. So what is gain margin now? 56 dB. Now what is phase margin? Is equal to 180 plus phi GC. You have got it here. So that is minus 90. So what is phase margin? Is equal to 90 degrees. Both of these are positive, then the system is stable. I guess Varsha, now we have understood. Hasya, do you still have any doubts? Varsha, if you have understood, just let me know. If you still have doubt, I am here to clear your doubt. You need not worry. We'll just move this. Maybe you may not be able to see this. Yeah, just look at this. Yes, clear, sir. Very good. Very good, Varsha. Hasya, do you have any doubts? Sanjana, do you have any doubts? Kishore, Shivakumar? Hope the concept is clear to you, Hasya. Clear, sir. So you can approximate, Hasya, that doesn't change anything much. Maybe there might be a small change, but that does not much affect the gain and phase margins. If it's gonna be positive, that will be a positive with a slight change in gain margin and also slight change in the phase margin. But no, sir, clear. Very good, Sanjana. No doubt, sir. Meghana, very good, clear. Very good, Meghana. Yes. So this is about Bode plot. If you still have any doubts and if you want me to solve any problem, you can also uh, tell me. We will solve in the next session, right? And in the next session, as a part of part B, we will solve polar plot one question and Nyquist plot one question, and then we will end this quiz quick revision of unit 3. Then we'll move on to the quick revision of unit 4. So once again, thank you all, Meghana, Sanjana, Hasya, Varsha, Soumya, Shirisha, Shiva, Vicky, Kishore. Once again, thank you all for joining me today on this session. Hope you had, okay sir, thank you Meghana. So hope you had a very good session today. And this today we have learned board plot and some introduction of the concepts of this board plot. Thank you Varsha. Hope you'll join the session tomorrow as well. Tomorrow we have thank you so much, sir. Very good, Hasya. Thank you, Hasya. Thank you, Sanjana. So tomorrow we'll be joining. Tomorrow we have a session at 11 a.m. on chapter 3, polar and Nyquist plot. So I want you guys to join me tomorrow as well. So as a part of part A, chapter 3, we have learned what is Bode plot and a problem on that, basic introductions. And once again, thank you all. And this is what I actually wanted to show you. So we'll also see that. Thank you once again. Yes. So as I always tell you, we have #1 study channels on Unacademy, and do like this video. Don't forget to share it to your friends, and also comment if you have any doubts, and do subscribe to Unacademy and Unacademy Semester Exams. You can use my code YSK10 to get the maximum discount on your subscription. You click on this bell icon to get more notification of my classes, and you can also join the Telegram group for more updates. So don't forget to like, share and comment on this video. Let's crack GATE and ESE with India's largest e-learning platform, Unacademy. Thank you. Thank you so much.